Grab a spring and pull. It pulls back. Pull harder and it fights you harder. The resistance grows in exact step with how far you stretch it. Hidden inside that everyday feeling is one of the most powerful ideas in physics, a force law. Today we uncover the force law of the spring, Hooke's law, and see how a handful of measurements becomes a rule that predicts the future. Forces come in several flavors. Some barely change from one instant to the next. We call these constant in time. Others barely change from one place to another, constant in space. The gravitational pull on an object near the Earth's surface is a fine example. Step across the room and it holds essentially steady. And some forces depend on the configuration of a system. Attach a mass to a spring and the spring force grows stronger whether you stretch the spring or compress it. The force responds to the arrangement itself. Some forces spread out through space, so their grip weakens with distance. Gravity and the electric force are the everyday examples. The gravitational force between two small objects falls off as the inverse square of the distance between them. Richer arrangements of attracting and repelling charges give forces that fade with other powers of r. Constant 1 over r squared, 1 over r cubed, and beyond. A force can even hold a steady magnitude while its direction turns. The gravitational force on a planet circling a star always points toward the center. That kind of inward attractive force is called a centripetal force. Notice the common thread. In each case, the force is tied to something we can measure, a position, a distance, a configuration. That is exactly what a force law is. A relationship between a force and some measurable property of the objects involved. Some interactions surrender to a clean force law, others resist it. To see how one is actually built from scratch, we turn to the spring. Here is the setup. An object of mass m rests on a horizontal surface. One end of a spring is fixed to a wall, the other end is attached to the object. Let L0 be the spring's equilibrium length, the length at which it is neither stretched nor compressed. We assume the surface is perfectly smooth, so friction cannot muddy the picture and the spring force acts alone. By Newton's third law, the force the spring exerts on the object is equal and opposite to the force the object exerts on the spring. That spring force is what we set out to measure. First, a coordinate system. Place the origin at the contact point between the spring and the object when the system sits at equilibrium. Let the unit vector I hat point in the direction the object moves as the spring stretches. The coordinate x marks the object's position from that origin. Picture 3 snapshots side by side. The spring at equilibrium with x at 0, the spring stretched with x positive, and the spring compressed with x negative. In every case, x is measured from the same equilibrium contact point. Now run the experiment. Stretch the spring until the object sits at position x, release it, and measure the object's acceleration at the very instant of release. At that moment, only the spring force acts along the surface, so Newton's second law gives it to us directly. The magnitude of the spring force equals the mass m times the magnitude of the acceleration. Measure the acceleration and you have measured the force. Repeat this across a whole range of stretches and compressions, from a maximum stretch Xmax greater than 0 to a minimum compression Xmin less than 0. A striking pattern emerges. Over that range, the magnitude of the measured force is simply proportional to the amount of stretch or compression. The magnitude of the force equals k times the magnitude of x. The constant k is the spring constant and it carries units of newtons per meter. It tells you how many newtons of force each meter of stretch demands. Direction matters too. Draw the free body diagram of the block. Displace the distance x from equilibrium. The spring force points back toward equilibrium. Pull the block right and the spring pulls left, push it left, and the spring pushes right. Writing the x component, the spring force is F sub x equals minus kx. That minus sign is the whole story. The force always opposes the displacement, always driving the object back toward x equals 0. A force that always points back toward equilibrium, like this, is called a restoring force. Plot it, and the law becomes a picture. Put the x component of the spring force on the vertical axis and the displacement x on the horizontal axis. The data fall on a straight line through the origin, sloping downward, with the maximum stretch x max, and the minimum compression x min marking the ends of the valid range. The line's slope is negative k, so the spring constant k is exactly the negative of the slope of force versus displacement. The steeper the line, the stiffer the spring. Now swap in a different spring and run it all again. The same clean proportionality appears, force rising linearly with stretch, though the value of the spring constant may be larger or smaller. A stiff spring has a big K, a floppy one has a small k. The shape of the law holds, only the number that labels the spring changes. Here we reach the pivotal move. It would be hopeless to test every spring that exists or ever will exist, yet a modest sampling keeps confirming the same relationship. So we take a leap. We infer that all ideal springs produce a restoring force proportional to their stretch or compression. A relationship observed for a finite handful of springs is generalized into a universal mathematical model. The force law we call Hooke's law. This leap from the sampled few to the universal many is called Newtonian induction, and it is the move that makes physics a predictive science. Watch what the leap buys us. Take a spring attached to an object of mass m and stretch it by an amount delta x. Using the force law alone, with no measurement of acceleration, we predict the force. The magnitude of the force equals k times the magnitude of delta x. Then Newton's second law hands us the acceleration for free. The magnitude of the acceleration equals the magnitude of the force divided by the mass, which is k times the magnitude of delta x, all divided by m. We have forecast the motion before touching the apparatus. Then comes the reckoning. Carry out the experiment, measure the acceleration within your error bounds, and compare it against the prediction. If they agree, the model stands. If the measured acceleration disagrees with the predicted one, the force law needs modification. This willingness to adjust, correct, or even reject a model in the face of new evidence is precisely what lets our description of forces reach into ever larger domains. Real springs add a wrinkle. Many are wound so tightly that you must apply a threshold force before they yield at all, a force of magnitude, F0 before the spring begins to stretch, and a force of magnitude, F1 before it begins to compress. These thresholds are the spring's pretensions. To honor them, Hooke's law splits into two cases. For positive x, the force is minus F0 minus kx. For negative x, the force is plus F1 minus kx. The two pretensions, F0 and F1, need not be equal, and like the spring constant, both are pinned down by experiment. Step back and see what we built. A force law ties a force to something measurable. For the spring, that law is Hooke's law, a linear restoring force, F sub x equals minus kx, with the spring constant read straight off the slope of force versus displacement. From a few careful measurements, Newtonian induction lifted us to a rule that predicts forces and accelerations we never directly measured, and it stands ready to be revised the moment nature disagrees. That is the engine of physics. Measure a little, model boldly, predict widely, and always let experiment have the final word. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.